Hello scholars, and welcome to Skill 15, Higher Order Factoring. Let's dig in. Our objectives for this lesson are that by the end of the lesson you will be able to identify which methods are needed to factor a quadratic based on the number of terms, and to factor higher order quadratics. As always, if you need time to catch up or you're falling behind, feel free to pause the video and rewatch things. Again, before we go into this, you should be familiar with the methods that we use to factor a quadratic. Now, when we talk about higher order, what does it mean? What we mean is that we're going to use more than just one method to factor a quadratic. So that means that we may have to factor a difference of perfect squares or perfect cubes, and after we factored it, the trinomial that is left over may be a trinomial that we can factor, and we need to check that. So here are our steps for factoring a higher order quadratic. We put the quadratic in standard form, then we look for the greatest common factor. After we factor out our greatest common factor, we factor the expression completely, and then we check to see if it can be factored again. Here is our factor tree. If you follow the methods explained in this tree, you can factor our higher order quadratics. So the first thing we're going to do is identify the GCF. Then we're going to look for the number of terms. If it is a binomial, which means it has two terms, it'll fall under the category of a sum or difference of perfect cubes, or the difference of perfect squares, if it can be factored. A trinomial will have three terms, and we will use our ACB tree, and then we will group by factoring, or factor by grouping, sorry. And if a polynomial has four terms, then we will factor by grouping. Alright, so let's try an example. Say we have x to the fourth minus 3x squared minus 4, and we want to factor this completely. The first thing I'm going to do is write my expression in standard form, and my quadratic is in standard form, so I don't have to change anything. It's just going to be x to the fourth minus 3x squared minus 4. I'm going to look for a greatest common factor. I don't see one, so my greatest common factor is just 1, or there isn't one. And now I look at this, my number of terms. I see 1, 2, 3 terms. 3 terms makes it a trinomial, which means I'm going to use my ACB tree. So I'm going to look at A times C. My A is x, or what my A is the coefficient in front of x, and my C is over here. And I'm going to look for what adds to the B, which is my coefficient attached to x squared. So I have negative 4 times 1, which is negative 4. And I want to see what two factors of this adds to negative 3. Well, negative 4 times 1 equals negative 4, and when I add them together, I get negative 3. So these are the terms that I'm going to be using. Now I'm just going to rewrite my expression here. X to the fourth minus 4x squared plus x squared minus 4. Now I remember I'm keeping my x squareds because they need to add up to 3x squared. So my exponents are going to stay the same here. Now I have 4 terms, so I can factor by grouping. Just going to group my terms up real quick. And from there, I'm going to look for what I can take out of this first term. And I see that I can take an x squared out. That gives me x minus 4, or x squared minus 4, forgive me. Plus, and I'm going to look at my second term. It already matches, so I don't have to take anything out. I'm just going to write a 1 here. That's going to be x squared minus 4. Now I can rearrange my terms. That gives me x squared plus 1 times x squared minus 4. Now I'm going to look at this, now that I'm done, now that I've factored this completely, and see, can I factor it again? Well, if I look at x squared minus 4, what I see is that is actually a difference of perfect squares. So my difference of perfect squares is a squared minus b squared is the same as, is equal to a minus b times a plus b. That was one of our formulas on the tree. So I can take this and break it down even farther. Now I'm going to rewrite it again. X plus 1 my x squared minus 4 can be rewritten as x minus 2 times x plus 2. And now I'm going to check again. X squared plus 1 I cannot break down anymore. I cannot factor it anymore, so I am done. And now I'm going to try 8x to the 4th minus 52x squared minus 180. Again, my expression is already in standard form. When I look at these terms, I see that they're all divisible by 4. So I can factor out a 4. And that leaves me with 2x to the 4th minus 13x squared minus 45. And now that I'm only going to pay attention to this trinomial inside the parentheses, I'm going to use an ACB tree to factor it. So I'm looking for 2 times negative 45. And that equals negative 90. And I'm looking for the terms of negative 90, the factors of negative 90 that add to negative 13. I know that negative 18 times 5 is 90, and they add together to equal negative 13. So those are the two terms I'm going to use. I'm just going to rewrite my expression here. 2x to the 4th minus 18x squared. Remember to keep your x squared because it needs to add back up into your middle term. Plus 5x squared minus 45. Now I have 4 terms, so I can factor by grouping here. I'm just going to group my terms right there like this. And I can factor out a 2x squared here, and that's going to give me 2x squared times x squared minus 9, sorry. And I want the other side to match, so I'm going to factor out a 5x, or I'm just going to factor out a 5 there, and that's going to give me x squared minus 9. And now both of my terms match. I can regroup my terms here. I have 2x squared plus 5 times x squared minus 9. And I bring my 4 down. Now I'm not done yet, because if I look closely, I see that x squared minus 9 is a difference of perfect squares. And again, perfect squares, a squared minus b squared is equal to a plus b times a minus b. So I'm just going to rewrite that part right now. So I'm going to have 4 times 2x squared plus 5 times x plus 3 times x minus 3. Now I see that I am done and I can finish my factor. Let's try another one. Let's try m to the 6th plus 4m to the 3rd plus 3. Again, I'm already written in standard form, so I don't have to change anything. And my greatest common factor is once again 1. I can't take anything else out of these. So it is a trinomial. I'm going to use my ACB tree. And my coefficient on A is 1. My constant is 3. Which gives me 3. And I want the factors of 3 that add to 4. Well, that's 1 and 3. So I'm going to rewrite my expression. M to the 6th plus 3 m to the 3rd plus m to the 3rd plus 3. Now I have 4 terms, so I can factor by grouping. Just group my terms like this. And in my first set, I can factor out an m to the 3rd, which gives me m to the 3rd times m to the 3rd plus 3. And that is going to be plus a 1, which is m to the 3rd plus 3. Now I can regroup my terms. M to the 3rd plus 1 times m to the 3rd plus 3. Now if I look closely, I can see that this, my first term right here, is actually the sum of 2 cubes. 1 cubed is still 1. So I'm going to have to go ahead and use my sum of 2 cubes formula. Our difference, or our sum of perfect cubes is a to the third plus b to the third is equal to a plus b times a squared minus a times b plus b squared. And now I'm going to just plug in my values here. So once I factor this, I'm going to get m plus 1 times m squared minus 1m plus 1 times, I can't forget to bring down my extra here, times m to the third plus 3. Now I know that I am completely done because there's nothing I can factor again. So we take our example number 4 here, and we see c to the 6th minus t to the 6th. I'm going to consider that as already in standard form, and my greatest common factor is going to be 1. Now I am going to consider c to the 6th minus t to the 6th as a binomial that is a difference of perfect squares. And I'm going to show you how I came to that solution. So I look at c to the 6th and minus t to the 6th, and what I see is that I can split this up. I can make c to the third squared minus t to the third squared. That makes 2 perfect squares that are being subtracted. And so I can simply rewrite this as c to the third plus t to the third times c to the third minus t to the third. Those are my difference of 2 perfect squares. Now I've factored, but am I done? No, because if you look at these are both a sum and a difference of a perfect cube. So we're going to need to use both of those formulas to get towards our end here. So I'm going to take a second, and then I'm going to reveal how I solve for this. What I would suggest you guys do right now is try to work out the problem and remember to use the formulas. So please pause the video and then come back when you're done. Okay, so the first half of my unfactored expression is a sum of perfect cubes. So I'm going to use the formula a to the third plus b to the third equals a plus b times a squared minus ab plus b squared. And then the second half is a difference of perfect cubes, which means I'm going to use the a to the third minus b to the third equals a minus b times a squared plus b times a plus b squared. And once I've plugged my variables in, I have c plus t times c squared minus c times t plus t squared times c minus t times c squared plus tc plus t squared. And now I am completely factored. And for my final example, suppose we come across something like this, x to the 6th minus 1. Now this is already in standard form, as all of our examples have been up until this point. They may not be, you're going to have to keep checking. My greatest common factor is still 1, but I'm going to treat this, just like I did in my previous example, as a binomial of perfect squares. Difference of perfect squares. So I can treat x to the 6th as x to the third squared minus 1 squared. And that is the same as x to the third minus 1, or plus 1, times x to the third minus 1. Now x to the third minus 1 is a difference of perfect cubes. As you can recall, negative 1 to the third is negative 1. So we can treat this as a to the third minus b to the third is equal to a minus b times a squared plus b times a plus b squared. And x to the third plus 1 is a sum of perfect squares. So it turns out just the same as we did our previous example. A to the third plus b to the third equals a plus b times a squared minus a times b plus b squared. Now I'm going to go ahead and give you guys a second to let you fill in the last final factor. Okay, and after completing my sum and difference of perfect cubes respectively on my left and right half of my factored equation, I come out with x plus 1 times x squared minus x plus 1 times x minus 1 times x squared plus x plus 1. And I am solved. I cannot factor this expression any farther. Thank you for coming today. If you have any questions, feel free to go back over the video, and good luck with your factoring. I'll see you guys in class.